Okay, so now let's look at a slightly different example instead of just point mass, and actually have something with a non-trivial moment of inertia. Okay, so we'll actually look at, for example, what's called a flywheel. We can have it connected, so it's just a wheel that is very easy to spin. So it can spin around its axis, and we will apply a force. So imagine connecting two pieces of string over here, and there is one string that's going to yank it this way, and one string that's going to yank it perpendicularly downwards this way. So let's say this is yanked 30 degrees from the tangent over there, like this. Okay, so let's call this T tension, and this is another tension. Let's call it T1 and T2, so they're different, and this is just yanked sort of perpendicularly from its axis. Okay, right? So it has, and this has radius R1, R2. Okay, we'll plug in numbers at the end if you want. Let's see. So you have a similar example in 10.7 in the textbook. So maybe I'll use similar numbers over there, which is, it says 50 newtons, and this guy's 50 newtons with SI units. And then it says the radius is 30 centimeters and 50 centimeters. All right, so the shorter one is 30 centimeters, this is 50, but immediately, if it's possible, immediately translate that to SI. So this is how I solve problems. Now this is in meters and newtons, so everything's fine. So I want to find the acceleration of this guy, okay? So someone's yanking this wheel that way, someone's yanking this way. So first of all, do they both make it rotate, or do they make it rotate the same way or different ways? Are they helping each other, or are they so counteracting each other? Well, this one's rotating it. You can imagine this guy's rotating it clockwise, and this guy's going to rotate it counterclockwise. So they kind of are opposing each other. Okay, so just to get an intuition first. Okay, and also try to train yourself, instead of thinking clockwise and counterclockwise, think into the board or out of the board. Okay, so T1 is going to cause it to rotate. Which way should your thumb point? It's going to rotate this way, right? Clockwise. So you want to use your thumb doing this way. So this one is going to create a torque into the board. This guy is going to create a torque. It's rotating it this way. It's going to create a torque out of the board. Okay. Yeah, so we'll try to find this acceleration. Okay, so because once we have the acceleration, the angular acceleration, we can use suvat to find everything else we want. Okay, so so we'll find the net torque, which is torque from 1 plus torque from 2. Okay. I'll again show you, should I show you both ways? Yeah, I'll show you both ways. So I'll do the full vector way, and also a way you can sort of get away with vectors as well. So let's call that method 1, method 2 without vectors, but slightly more thinking. There's always a trade-off between this. So all right, so with vector, sort of less thinking. You just go on and plug in the numbers. All right, so that's tau1 and the direction. Be careful the difference between tau and t. There's a tension. That's not the torque. Okay, so this is into the board. So let's define the axis. So we're gonna do into the board is, are they both the same numbers? I just want to be the same as the book. Okay, yeah. So into the board is gonna be positive k. Again, it doesn't matter. I usually do out of the board, but I'll do it this way. It's just to show you doesn't matter, right? As long as you're you know what to do. So T1 is going to create a torque into the board. It's going to do it this way, right? So the torque created by T1 is going to be positive k, and the torque, the magnitude, so it's the magnitude times it's going out of the board. So into is, this is really counterintuitive for me. So usually, so I'll draw extra symbol, right? So the cross means into, right? So this one's negative k. Yeah, I usually call this positive, but we'll work with it. We'll see, right? So what do we have? We have tau1 minus tau2, right? Essentially, before we plug in the taus, right? So now I just need to plug in the magnitude of them, because the direction is taken care of over here. Okay, so now we have, so here we need to take into account this angle here, right? So this one's slightly easier. In fact, yeah, let's do them one by one. So the tau one is the magnitude of R1 cross T1. Agree, right? And this is the magnitude of R2 cross T2. Okay. So there's a couple of ways you can do it. You can use just blindly with vectors and just apply the formula. So this is R1 T1 sine theta, theta being the included angle between the R vector and T vector. So T vector is here, the R vector is here, but they're not together. How can you find the included angle? I don't know. Well, you need to move this up. So they're at the same point, right? So the displacement from the axis to the point. Now they are at the same point. You just translate this up here. This should be the same length, but just imagine that in your head. You can now talk about included angle, right? The included angle is 30 degrees. No, the included angle is 60 degrees, right? So here you're gonna plug in R1 being 0.5, T1 being 50, and here you're gonna put sine 60 degrees for this guy. And subtract by R2 T2 sine theta. So this is R2. Again, you need to compare. So pull it, just shift this a little bit to here. Okay, so now you can talk about the included angle, which is 90 degrees over here. So this guy is minus R2 is 0.3, 50, and sine 90 degrees, like that. Okay, which is just 1. Okay. Okay. Let's use square brackets. Okay, so yeah, so now you have 0.5 times this, so that's half of this, so that's 25 times sine 60 is √3 over 2 minus 0.3. What's 0.3 times 50? So what you can do is the 0 shifts this over here, so the 10 times 0.3 makes it 3, so now it's just 3 times 5, so that's 15 and 1. All right, so you get this. And now you can plug everything into the calculator, and I think you should get 6.7. All right. So let's just see which do I get negative or positive? 6.7. I think I will get positive 6.7. Yep. 7. Okay. What's the units? This is Newton's meters, essentially, right? Newton meter. There you go. All right, so what does that mean? I have positive K, so it's positively into the board. So it's this way and this way, all right? So it's rotating that much torque clockwise, all right? But I want to find the angular acceleration. So we need to take the net torque and match that to the I alpha, okay? So I'm finding that I want to find the angular acceleration for this guy. So first of all, we know that it's into the board, so it's actually clockwise, all right? Now we need to we want the angular acceleration of the system. So we want the net torque on the system. So this is Newton's second law, and we want the I of the system, okay? So what is the I of the system? This is not point mass now, right? This is a whole disk. So the whole disk is, yeah, you now need to consider it as a disk. So here you are rotating it at this point. So you need, so imagine you are basically rotating 2 wheels, okay? You're rotating this wheel and this wheel, all right? So let me look up the formula for the moment of inertia for wheels again. Okay, so I've looked up the disk is the I for a disk is 1/2. It's always going to be mr squared, but it's very easy to forget the 1/2 or whatever it is. So this is the part where you will be given a table to look up. All right. So for this, that's the moment of inertia. And I also don't need to split into 2 disks. I double check the book. This is just one big disk. It's not a small disk with a large disk. So the whole system is just one disk. Okay, yeah. So here I have 1/2 m, and the radius, which one is the radius of the disk? It's r1, r1 square, and we have a over here. Okay, good. So and tau is the net torque is 6.7, right? 6.7 in the positive k direction. Now the alpha is also, so just like A is going to be in the same direction as F, alpha is going to be in the same direction as torque. So I can also, yeah, I don't have to worry too much about the direction, but we can keep it because we'll just work with full vector strategy first, right? So here we have 1/2, and the mass of the whole thing, the book actually hasn't given that, so I'll just make up an easy number like 10. So let's say the whole thing is 10 kilograms. So we'll put 10 over here, and this is 0.5 square. Okay, so now you plug this in the calculator. So yeah, let's pull this up and see what we have. So we have so 6.7 times 2 divided by 10 and divide by 0.5 divided by 0.5. Okay, so that's 5.36. Okay, so this is the alpha, and let's plop in the unit. You can put it here, you can put it here, that's fine. And what's the unit? Radians per second square. Right, good. So this is positive. That means which way again? It's into the board, so it's rotating clockwise. So if you want to make sure that's clear, you can put down clockwise as well. Okay, so yeah, and then you can find out, so I can now ask you if it starts at rest, and I start yanking it with these two forces constantly, with a constant force of this, so we have a constant acceleration, then how we can use SUVAT to find out how much it has rotated. Okay, yeah, so this is in general how you solve it. With you can see sort of a strategy without vector is you don't need to put this in, and you can just think about the direction and directly jump to this step. It's a little bit more thinking, but it's a little bit less writing. So you can jump directly to this step and say, okay, so let's start over, right? To find the net torque, you can say, I want to find the net torque. I'm going to define the direction in clockwise. Okay, so it's going to go into the board is positive. So essentially, I'm going to write down this equation as if it's clockwise. I'll give you an analogy with the force that you've done before, right? It's just now it's clockwise or counterclockwise. So it's like saying I have two forces over here. Let's make this shorter, right? So this is 20, this is 5. So I can just say, what's the net force? The net force is to the right is 5 minus 20, all right? So it's negative 15 newtons to the right. Or you can say, someone else can come along and say, hey, the net force in the left direction is 20 minus 5. So it's a little bit more thinking, right? So you need to sort of think which one's positive, which one's negative, or you can just blindly go, I'm going to define this side as x, and I'll just do the vector way. So force 1 plus force 2. This one is 5i hat. This one is negative 20i hat, like that. And then you go, the answer is minus 15i hat. And then, so you have sort of two ways, you have almost three ways to do it. You have the pure vector way, which you just do, oh, it's a vector addition. There's no subtractions at all with pure vector, as we talked about in week 2 or week 3. And you can do it with the directions, but now it requires a little bit more thinking. Should I do 5 minus 20 or 20 minus 5? Depends on your direction. So here we can do it without vectors and a little bit more thinking with clockwise. So clockwise is going to be T1, and also it's only going to be this component of T1. Right, so it's T1 parallel, sorry, parallel, yeah, it's perpendicular to the radius, but parallel to the wheel. So let's call it tangential. So T1 tangential is the one that's gonna cause the rotation, because this guy is not gonna cause any clockwise motion, right? It's T1T that is causing the clockwise rotation. So it's that times that. So you can yeah, but essentially it's the magnitude of that. So you almost directly go into resolving this guy. Right? So T1t is sine of 60. So you go T1 sine 60 degrees. And R here is, yeah, so it's this one times this one. Just remember the formula again. So torque, right, is R times force perpendicular to the displacement vector. Right? So it's this one essentially. So it's T1t times R. So in our case, we want R1 times T1t like that. So it's R1 T1 sine 60 or cosine 30, as you can see, it's the same thing. And it's clockwise. So we're analyzing it clockwise. And then this guy's counterclockwise. So you're going to subtract this guy's effect, which is going to be R2 times, now this is already perpendicular to R2, like T2 is already perpendicular to R2. So we can just go R2 T2 like this, or sine 90 degrees, right? So can you see we have jumped immediately to step 5. I think I missed a K as well over here. Yeah. So if you do it this way, you can say, hey, I'm writing down an equation for clockwise. So the torque is this much in the clockwise direction, and this much is the counterclockwise. So we do the subtraction just like how we did it there. So you already skipped to this step, and yeah, and then you go and plug in the numbers: 0.5, 50, root 3 over 2, or put in the calculator, minus 0.3, 50. And put this in the calculator, you'll get this, right? 25 times root 3 over 2 minus 15, right? So you'll get 6.7. And this time you'll see it carries forward. Whatever you set here, clockwise, right? It stays clockwise over here. And there's no more vectors, but it requires a little bit more thinking, right? So pros and cons with both sides. I'll encourage you to sort of get used to both, know how to do both. And whichever is more convenient to you, yeah, you can use it. For me, my personal advice is, I think when I do a lot of these problems, this is what I prefer. But when I come to something that the question changes a little bit and it's not in the same pattern, then to me, it's easier to think about it with the vector, because now I know it's always correct and I don't need to sort of have additional thinking. But anyway, that's my take on it. Yeah, both ways works, and depends on how much problems you do. Are you the type of person who rather do a lot of problems, sort of get used to it, and then this is more efficient, or do you rather focus on understanding the concept very well so you can almost figure it out from first principles using your understanding, and then you might prefer the vector way because that's sort of more mathematical. All right, so yeah, that's my take on it, and we'll comment on the last two things of this long journey. You basically now know the Newton's law, so of the rotational version, right, of this. And yeah, you can just to tell you what type of problems you'll see. It's sort of if I'm rotating a sphere this time, then you will have, right. So I alpha equals to the net. That's new Newton's second law for rotations, but this time you put in the sphere, and then you can get the alpha for the sphere and this for the sphere. And if you want to know a certain tangential acceleration over here, and you can now relate the alpha, the tangential acceleration, with the radial acceleration like this as well, in what you've learned in the previous lecture. And then you can see, so that's the R, and you can, so if I know what the alpha is, like let's say 5 radians per second squared, right? And you want to know the tangential acceleration at this point, you can just multiply 5 to, let's say 0.5 again, 0.5, 0.5 is 1.5. So this is 2.5 essentially. And you will get this is the rim over here, right, on the surface, or the rim of the sphere of the basketball or whatever. Except this part has a tangential acceleration of 2.5 meters per second, and you can see whatever. There's a whole lot of variety of questions you can be asked. But all of them can be now predicted and calculated this way. All right, so we'll look at the last two is angular momentum and angular kinetic or rotational kinetic energy.